So the nice thing about least squares linear regression is that it's actually very versatile. So you might think that this is a bit of a simplistic model if we have to assume that we're drawing a line through our data or a hyperplane through our data, and that's all that we're allowed to model our data with using linear regression. But recall that linear regression is it's called linear regression because the output is linear in the weights. So we have a linear function of the weights, not necessarily of the inputs x. So here's, for example, a problem where linear regression is not going to be something that we want to do as we've been discussing it so far, but we'll see how we can modify it very, very easily in order to handle this problem as easily as modeling it with a line. So if we look at the original linear regression model that we've been formulating thus far, we again have the output y is approximately equal to the input x times some weight w1 plus an offset w0, which is simply the intercept term. So we're basically saying that the data has to be modeled by a line in this case. And of course, for this particular data set that we're looking at here, that's not an ideal function. We can see clearly that the data does not follow a line. So we would want some sort of more complex model, more complex representation of how the inputs relate to the outputs. So for example, and this is how the data was generated, we could say that the output is now equal to some offset plus a weight times the input x. So again, the input is just one-dimensional, plus another weight times the input x squared, plus a third weight times the input x cubed. So a third-order polynomial. So notice that in this case, we're taking our data, our input x, and performing a function of it to take it from one dimension to now 3 dimensions. So we have 3 kind of views of our input x squared, and x cubed. And we're multiplying each of those by their own separate independent weight, w1, w2, and w3. And according to this model, we can take our input, for example, the input 2, perform this function. So we have 2 here, 4 here, and 8 here. And then using those 4 weights, we would get this output. And if we sweep all these values, we get this sort of a third-order function. So can we use linear regression, least squares linear regression, everything that we've been talking about thus far, to learn this problem? And so the answer is yes. It's very simple. And we end up with something called polynomial regression, which is simply taking your inputs x, performing some polynomial, some function, a particular function on that, and then doing least squares linear regression on the polynomial that you construct from the inputs. So in this case, let's go back and let's ask why can we use everything that we've been doing thus far with minimal modifications. So remember that the definition of linear regression is that the function f is a linear function of the unknown parameters w. It doesn't have to be a linear function of the inputs x, only of the parameters vector w. So therefore, a function such as this second-order polynomial is still a linear function in w, even though it's not a linear function in x. And so what we'll find is that we can actually do least squares and learn exactly the same solution, the only difference being that the matrix x has a little bit more preprocessing in order to construct it. So let's look at a simple case of data x coming in R. So we have one-dimensional inputs, and we're using that to predict a one-dimensional output. This is exactly like the previous slides we've been looking at. And we want to learn a pth-order polynomial approximation of the relationship between the input and the output. So very quickly, let's look at how can we do this. So let's construct the matrix X, where again we put in the first column a column of ones for the offset. In the second column, we then put the original data, x1 through xn. In the third column, we then take those inputs and square them. So we have x1 squared through xn squared. And if we want to learn a pth-order polynomial, we continue that up until we get x1 to the p through xn raised to the p. And then we solve this exactly as before, and we can approximate the output y. For example, if we look at the output y as being this vector through yn, we can then say that y is approximately equal to x times a weight vector, where, for example, if we look at y1, we're saying that's approximately equal to 1 times w naught plus x1 times w1 plus x1 squared times w2, and so on. And so we're basically approximating the output of y1 as a pth-order polynomial of the inputs x1. So then if we set this approximation up and we want to now learn w using least squares, we follow exactly the same procedure as before, and we learn that the least squares solution is x transpose x inverse times x transpose times y. Except now, even though the inputs are one-dimensional in this case, the matrix that we've constructed is p plus one-dimensional. And so this vector, WLS, is a p plus one-dimensional vector, where the first dimension is the offset, the second dimension of w corresponds to the weight on the input x, and the third dimension of w corresponds to the weight on the input x squared, and so on and so on. And so that's a simple way that we can model a polynomial function of the inputs using least squares linear regression, where all we have to do is perform this pre-processing to construct our matrix X. So here we have a one-dimensional input X and a one-dimensional output, call it T. We have 10 data points, so 10 pairs of inputs and outputs indicated by these blue circles. And then we want to learn a 0th order polynomial. What does this correspond to? This corresponds to the DC offset W naught. So we don't even use the data. We simply construct X as a column of ones. So in this case, we're looking at this matrix where a 0th order polynomial is simply this first column, and we have nothing else here. And this is what we learn. This is the least squares solution if all we're allowing ourselves is a shift of the axis, a shift of the offset. Now let's go back to what we've been discussing, which is what we had earlier discussed, which is least squares, where we have a linear relationship of the inputs to the outputs. In this case, we get this line, and our matrix, again, X, is simply a matrix of all ones in the first column, and then the data in the second column, and then we perform least squares to learn W naught and W1, and we approximate the data with this function here. If we then want to expand this to a 3rd order polynomial, so in this case our data looks like this, where we have ones in the first column, the original data in the second column, and then up to the original data cubed in the 4th column. And we perform least squares linear regression with this matrix X. We learn 4 weights in this case, and now we approximate the output as a third-order polynomial on the inputs, we get this sort of a function here by the red line. So what we would do, just to remind you, is we would take our input, we would then predict this unmeasured value by taking the input, squaring it, cubing it, having these three numbers, and then saying that this value is equal to W naught, which is corresponds to the first column, plus W1 times this value x here, call this x11, plus W2 times x11 squared, plus W3 times x11 cubed, sum those three values up, and we would get this value along the red line. Okay, so we can try to be clever and push this. Instead of learning just a third-order polynomial, how about we try a ninth-order polynomial? So in this case, clearly things start to break down. And why would this be? Because in this case, the matrix X is 10 by 10, because the first column of X is, again, all ones. But we have now 9 more columns of the data up to a ninth-order polynomial. So our matrix is now 10 by 10, meaning that we can easily learn a 10-dimensional vector that passes through all 10 of these points, because we are trying to predict a 10-dimensional output y as approximately equal to x times a weight vector w. And if we have 10 outputs and a 10 by 10 matrix, assuming that this is full rank, we can easily learn a vector that perfectly reaches or touches all of these points, that passes through all of these points. But we see that in the regions in between the points, for example here, we're going to be way off. And this is an example of overfitting. So what we've done is we've overfit our data. So we've basically perfectly predicted our training set of 10 points. And as a result, because of this overfitting, we're way off on new points. And so this is a caveat about modeling and using more and more variables or more and more parameters to better model your training data. The better you model it, at some point you'll start to overfit, and we'll discuss this a little more later, where you're now doing very well on your training set, but you're doing very, very poorly on your testing set, which would be a new point, for example, this one here. Okay, so we've been discussing polynomial regression in one dimension. Let's just extend this to 2 dimensions to see the logic of going to higher dimensions, and hopefully after 2 dimensions it's straightforward how you would do this in n dimension or d dimensions. So, for example, if we wanted to do a second-order polynomial regression model in R2, what we would have is, for the ith observation, we would model that as approximately equal to an offset W naught plus the linear regression problem W1 times the first dimension of xi plus W2 times the second dimension of xi. So this is the original linear regression problem we introduced at the beginning. And then we take those 2 dimensions and square them and then put 2 more weights on those squared values. With third-order polynomials, what we would have is the same thing, and then we would take each of those values and cube them and then put 2 more additional weights because we have 2-dimensional inputs. And so in general, the width of this matrix X that we're going to construct grows as the order of the polynomial times the dimensionality of the input vector x plus 1 for the offset. So if we look back at the original problem of how we can map the years of the amount of education and seniority versus a person's income using a first-order polynomial, in this case linear model on the inputs, we get a plane. We approximate the output as being a hyperplane, a noisy hyperplane, which is evaluated on the 2-dimensional inputs. If we now want to do a third-order polynomial instead, we get a function that can look like this, where we've simply taken the two-dimensional inputs, performed these squarings and cubings of their values, and turned it into a six-dimensional problem instead of a three-dimensional problem, including the offset. So what are some further extensions that we can do of this model? So really, as long as the function is linear in the weights, we can do any function of the inputs x that we can dream up and construct the matrix x, where on each column we perform some function of the original input vector x, little x. So more generally, if we imagine that we have inputs x that are in d+1, meaning the first dimension is a 1 by definition, we can define a least squares linear regression function to be of this form, where we simply say there are s weights, where s is variable. We then take, for each dimension of for each function that we're going to perform, we take our input and pass it through a particular function, call it gs. So this function gs takes our input xi and outputs a one-dimensional output, which is some function, and multiply that by a weight. So, for example, in the original problem that we looked at, we could have had gs simply takes the input xi and returns the sth dimension of it, meaning that this is simply taking a vector and picking out one of its dimensions, and that would give us the original linear regression problem that we looked at the beginning of the lecture. But there are more examples. So for example, we can define the sth function to be the square of the jth dimension, which is related to the polynomial regression that we've been discussing. We can define a function to be a log of the input of a particular dimension. We can do something that's not a continuous function. We can have an indicator that is equal to 1 if the jth dimension is less than some number a, or equal to 0 if it's greater than or equal to a. Or we could even compare dimensions of our inputs and define the sth function to be an indicator of the jth dimension being less than the j prime dimension, the j primeth dimension. So there's a wide variety of functions that we can perform. This is where domain knowledge and expertise would come into play, where you believe that there are certain relations between your dimensions, between the dimensions of your data and the outputs. For example, you don't think that it should be linear in the input, you think it should be a logarithmic in the input. So you can perform any function that you can define, and as long as it's linear in the weights, w1 through ws, we can construct a matrix x, capital X, by putting the transformed vectors of each xi along the ith row, adding a 1 to the first column, and then solving the least square solution, which always has this form. Of course, the caveat that we saw from previously with the ninth order polynomial regression function was that the more functions that we use, the more data that we're going to need to avoid overfitting.